Major depressive disorder, MDD, is a pervasive mental health condition affecting 300 million people worldwide, with a staggering 27% increase in global prevalence due to the COVID-19 pandemic. Current diagnosis methods, relying on clinical interviews and self-reported inventories, are subjective and prone to bias, resulting in a high misdiagnosis rate. Recent research has focused on using machine learning (ML) systems to automatically assess MDD presence and severity from clinical interview recordings. A growing body of research investigates multi-modal approaches, combining verbal and nonverbal cues to reach a diagnosis. These models achieve high success rates, typically incorporating audio, video, and text-based data. However, the text-based modality is often the weakest link due to scarce task-specific training data, hindering the effective training of NLP models. This work proposes a novel, Tri-Modal architecture that incorporates large language models, LLMs, to improve depression diagnosis from clinical interview recordings. The architecture utilizes Mel Frequency Cepstral Coefficients, MFCCs, facial action units, FAUs, and a two-shot learning-based GPT-4 model to process text data. MFCCs provide a compact representation of human perception of sound, allowing for the low-level representation of timbre, pitch, and rhythm. FAUs, a low-level representation of facial muscle movements, are effective for effective computing tasks. The proposed architecture outperforms baseline and state-of-the-art models on the DAIC-WOZ AVEC 2016 challenge dataset and leave one subject out cross-validation, achieving an accuracy of 91.01%, F1 score of 85.95%, precision of 80%, and recall of 92.86%. This work demonstrates the effectiveness of LLMs in multimodal architectures for mental health diagnosis and highlights the potential of such architectures in classifying depressed patients. Table I presents state-of-the-art multimodal fusion systems for binary depression classification, showcasing the performance of various architectures. This work builds upon existing research, incorporating LLMs into a multimodal framework to improve depression diagnosis accuracy. The proposed architecture is integrated into a locally hosted web application, emulating its potential use in real-world scenarios. In the context of multimodal depression diagnosis from clinical interviews, data fusion strategies play a crucial role in integrating information from different modalities such as audio, text, and video. Early fusion, late fusion, and model-level fusion are three prominent strategies used in machine learning models. Model-level fusion, which combines individual modalities before concatenation and further processing, is the most commonly used and best-performing fusion method for this task. The DAIC-WOZ dataset contains clinical interviews with various errors that needed to be resolved before preprocessing steps could be applied. These errors include the presence of research assistant interactions prior to the interview, missing therapist utterances, labeling errors, and incorrect transcriptions. To address these issues, the authors applied regex and NLP techniques to correct grammatical errors, identify interrogative sentences, and adjust speaker names for clarity. The text preprocessing steps involved converting CSV files into raw text data, merging subsequent utterances by the same speaker, and diarizing speakers by preceding each utterance with the speaker name followed by a colon. The audio preprocessing stages included segmenting audio to include only patient speech, augmenting audio data to increase sample size, extracting Mel Frequency Cepstral Coefficients, MFCCs, using LibroSA, and normalizing MFCCs using Cepstral mean and variance normalization. The DAIC-WOZ dataset also contains visual features extracted from video data using the Open Face Pose Estimation Library. Among these features, only facial action units, FAUs, were considered in this study. The dataset provides a binary label for depression diagnosis based on a Patient Health Questionnaire 8, PHQ-8, score, where participants scoring higher than 10 were considered depressed. The dataset was accessed after signing an end-user license agreement. The proposed model for detecting depression in clinical interviews uses a tri-modal approach, combining audio, visual, and text data. In the audio preprocessing stage, speech waveforms are windowed and transformed into the frequency domain using a fast Fourier transform, FFT. The magnitude of the FFT is then computed, and the data is converted into filter bank outputs. The log base 10 of these outputs is calculated, followed by a cosine transform to reduce dimensionality, resulting in Mel Frequency Cepstral Coefficients, MFCCs. These MFCCs are then normalized using Cepstral mean and variance normalization, CMVN, to account for variations in recording conditions. In the visual preprocessing stage, video data is segmented to include only periods when the patient is speaking. The segmented data is then sliced into 8-second segments, aligning with the segmented audio data. Continuous, non-discrete facial action units, FAUs, are normalized to zero mean and unit variance. For text-based model development, two-shot learning is employed with GPT-4 through the OpenAI API. The model is given a prompt to classify the patient as depressed or not depressed, based on the full text transcripts from the DAIC-WOZ dataset. A modified version of the prompt presented in Galaitzer-Levy et al. 2013 is used. The proposed model architecture, optimized by the hyperband tuning algorithm, consists of 7 steps to reach a classification. First, higher-level features are extracted from the MFCCs in 3 consecutive blocks consisting of bidirectional long short-term memory, BiLSTM, dropout, and batch normalization layers. The input FAU data undergoes 3 processing steps before concatenation with the MFCC tensor. A. Flattening into a 1D tensor. B. Repeating the flattened data for each time step. And C. Normalizing the repeated data. The final model is evaluated using Leave One Subject Out cross-validation, LOSOCV, where a unique model is trained for every clinical interview in the dataset, excluding all samples originating from one clinical interview. Each model is tested on the excluded clinical interview, and all model results are pooled for the final performance calculation. Augmented samples are not included in testing data. The proposed architecture integrates large language models and audiovisual features into a tri-modal architecture for diagnosing major depressive disorder, MDD, from clinical interview recordings. The model processes facial action units, FAUs, and Mel Frequency Cepstral Coefficients, MFCCs, using time-distributed and dense layers, followed by concatenation and processing by consecutive BiLSTM, dropout, and batch normalization layers. The processed data is then concatenated with the large language model, LLM, binary output and processed by 4 consecutive leaky ReLU-activated dense layers and 1 sigmoid-activated layer, outputting a binary classification. The proposed model was evaluated using the DAIC-WOZ AVEC 2016 Challenge Cross-Validation Split and Leave One Subject Out Cross-Validation, LOSOCV, outperforming all baseline models and multiple state-of-the-art models. The model achieved accuracies of 92.9% and 90.2% on LOSOCV for the depressed and non-depressed classes, respectively. However, the accuracy of 92.9% for the depressed class on the AVEC 2016 cross-validation split may be inflated due to the small sample size of 14 for the depressed class. The model was also integrated into a locally hosted web application, DEP-Scope, for easy and accessible use by clinicians. The application uses the Zoom Application Programming Interface, API, to retrieve clinical interview recordings and process them using the proposed model, generating clinical reports containing a summary of the interview and a justification for the diagnosis. The proposed model faces limitations, including its speed, which suggests it is not suitable for real-time applications, and the use of large language models, which may limit its deployment. The small and homogeneous dataset used in this study may have negatively impacted the generalizability of the model. Future work aims to optimize the proposed architecture for increased accuracy and make the model easily accessible to use. This research paper presents a comprehensive study on the development of a novel multimodal deep learning model for the detection and estimation of depression levels in clinical interviews. The proposed model integrates both auditory and visual cues, leveraging advanced techniques in speech recognition and facial expression analysis. The study highlights the importance of multimodal data fusion in improving the accuracy of depression diagnosis, as well as the potential benefits of using large language models to enhance the model's performance. The authors also emphasize the need for a more nuanced understanding of psychiatric diagnosis, moving beyond traditional self-reported measures and incorporating objective, multimodal data. They propose an innovative approach to integrating various data sources, including audio and video recordings, into a unified model. This approach is expected to enhance the reliability and validity of depression diagnosis, reducing the impact of information bias and other methodological limitations inherent in self-reported data. The paper also discusses the importance of addressing potential issues such as confirmation bias and social desirability bias in psychiatric diagnosis. These biases can lead to inaccurate diagnoses and hinder effective treatment planning. By leveraging advanced machine learning techniques and multimodal data fusion, the proposed model aims to mitigate these challenges and provide a more accurate and comprehensive assessment of depression levels. Moreover, the study highlights the significance of using large language models in enhancing the diagnostic capabilities of the proposed model. These models have shown promising results in various domains, including psychiatric diagnosis, due to their ability to capture complex patterns in language and generate contextualized representations of spoken words. The paper also presents a preliminary evaluation of the proposed model using a clinical dataset. The results suggest that the multimodal approach outperforms unimodal models, emphasizing the importance of integrating auditory and visual cues in depression diagnosis. However, the authors acknowledge several limitations and potential avenues for future research, including the need for larger datasets and further exploration of various multimodal fusion techniques.